So today I'm going to talk about the Bose-Fermi Auxiliary-Field Quantum Monte Carlo algorithm, which is an algorithm that I developed as a graduate student, as a slightly younger, less gray-haired graduate student, under the supervision of Professor David Reichman at Columbia University and Professor Shiwei Zhang at the College of William and Mary. As you can see from this figure here, recently atomic physicists have become interested in what happens to mixtures when you place them in optical lattices. What this algorithm attempts to do is to create a quantum Monte Carlo framework for studying such experimental systems based on first principles. So I should warn you, usually I don't give the mathy version of this talk, but today, since everyone's an expert, I will give you all the details. So I know many of you are very familiar with auxiliary field quantum Monte Carlo, and so I'll go through everything step by step. So please hold on tight if you're not familiar, and feel free to ask any questions. That said, I'll begin by introducing you to many cutting-edge experiments on mixtures in optical lattices. I'll then discuss a number of approaches that have been developed over the years to study these mixtures in lattices, and then tell you how our approach, the Bose-Fermi Auxiliary Field Quantum Monte Carlo approach, goes beyond where these other approaches have gone before, and hopefully enhances what we can predict about these experiments in the future. I'll then discuss some benchmarks that we have performed on these systems, just to ensure that the formalism I'm presenting to you is actually correct. So we see that our formalism is correct, and then as I'll discuss during the last part of our talk, our formalism faces a few challenges. So I'll go through those challenges and then discuss what goals we have and what kinds of things we hope to accomplish if we can actually surmount those challenges. So the starting place for much of this discussion is with optical lattices. Optical lattices are lattices made out of light. So around 30 years ago, atomic physicists realized that they could trap particles in these essentially laser waves using dipole forces. And by trapping these particles in a very clear pattern, they can form essentially very ideal solids. So because of the fact that you can control lattice intensities, you can control interference patterns, that means that you can very precisely engineer these lattices so that they are essentially perfect. They have no defects unless you actually want to create defects. They have no dirt, and so they serve as very basic model systems. And so with these lattices, you can study a number of the fundamental models of condensed matter physics. As I'll discuss shortly, you can look at things like Hubbard models and various other models as well in a very clean fashion that normal materials don't allow you to look at. Two of perhaps the most fascinating phenomena that these optical lattices have allowed physicists to study are the Superfluid-Mott Insulator Transition in Bose gases and the phenomenon of Fermi pressure in Fermi gases. About 10 years ago, in what I would call the most spectacular use of optical lattices to date, Marcus Graner was able to demonstrate that a delocalized superfluid can transition into a Mott insulator that's highly localized simply by lowering the lattice depth. So each of these, the lasers, creates a lattice depth that can be increased or decreased, and simply by increasing the depth of this lattice, you can transition into a Mott insulator. So this is expected on the grounds of let's say, studying the Bose-Hubbard model. You could readily predict this kind of transition. Similarly, for fermions, around the same time, Truscott et al. Were able to demonstrate the phenomenon of Fermi pressure. So what they did was they put bosons, Li7 in particular, and fermions, Li6, into magnetic traps and then cooled these systems down into degenerate states. And then they simply observed what happened to the clouds. And so for bosons, the clouds shrunk, which essentially is emblematic of them condensing, whereas for fermions, the fermions remained relatively dispersed. So after some temperature, they didn't shrink anymore. And so this basically shows that you can look at particle statistics within these traps. So given these successes, people have since begun to consider what happens to Bose-Fermi mixtures. The natural next question is what happens when you mix these two things together. And really the first and only set of experiments that have been performed so far question what happens when you put fermion impurities about 0 to 20%. Sure.
Question. So at the previous slide,
yeah.
answer this one.
Sure.
So the coupling
Mm-hmm.
here. So obviously, I mean, the external trap, but then what is the coupling between the fermions and between the bosons?
Oh, okay. So
strong coupling?
right. So in these cases, we're not talking about mixtures yet. So here I'm just talking about bosons. These are pure bosons.
Yeah.
So your boson-boson coupling.
Yeah.
So this is just based upon the scattering lengths for the bosons.
Pardon?
Based upon the scattering lengths for the bosons. So based upon the Feshbach resonances, you can control the scattering lengths.
Yeah, so it's something.
Right.
It's not necessarily strongly coupled.
Right. So here you're clearly there's a clear strong interaction because you're in the strongly interacting regime in order to get a Mott insulator.
Okay.
So you're at very low temperature. So the only way to get this quantum phase transition is with a relatively strong coupling. Okay, so with mixtures, basically by putting fermion impurities, they were able to demonstrate that you can decrease the visibility of the bosonic interference pattern. So here's a case of pure bosons, and you can see that they transition into a Mott insulator-like state. If you add fermions, this decrease in the coherence of the interference pattern happens more quickly. So this is really the only experiment, the only set of experiments that has been performed so far on these mixtures. And the key question is, what can we bring as theorists to the study of these mixtures? Can we guide experiments in any way? Can we actually influence these experiments in the future by providing theory that may guide them?
Sorry, what's changing from left to right in these three pictures?
Oh, so this is the recoil energy, ER. So this is basically a measure of how much kinetic energy, in some sense, the bosons have. That's the recoil energy in general. And here, this is just measuring the trap depth in terms of the recoil energy. So if you have a higher trap depth, that means the lattice depth is deeper, then you're going to have a higher multiple of the recoil energy. So you're just increasing the depth of your trap. So far, really the only theory that has been applied to these systems has been a combination of mean field and perturbation theories. And these theories basically predict a very rich phase diagram where you see a number of different phases composed of sort of Bose-Fermi composites. So you have a fermion that's coupled to some number of bosons, which is given by these Roman numerals. That's the number of bosons. And you can get density waves, you can get superfluids, et cetera, depending upon how you vary your chemical potentials and the ratios of your Bose-Fermi to your boson-boson coupling. But perhaps even more interesting than just having a large number of phases and a very nice phase diagram that you can try to delineate is the fact that these things are actually experimentally useful. So you can use bosons to sympathetically cool fermions. So we know that because fermions cannot elastically collide together if they're in the same state, and that's key if they're in the same state, people can instead use bosons to cool them to very, very low temperatures. And this can enable studies of very low temperature fermionic physics, such as the BEC-BCS crossover that everyone's interested in. We can also look at dipolar molecules. So this is something that's definitely on the agenda of experimentalists. If they can form these molecules, then they can study potentially long-range dipolar interactions on a lattice and look at phases caused by those interactions. And what theorists using mean field theory have basically predicted is that you can form supersolids, and also you can see enhanced superfluidity. So you can imagine basically forming a density wave based upon fermions and then having the bosons coupled to that density wave to form a supersolid. And it's been proven several times by several people, or at least suggested several times by several people, that if you have bosons, those bosons can mediate an attractive S-wave pairing among fermions. This is called the Cooper problem. And so you can enhance the superfluidity of those fermions alone. So these are some fundamental reasons why we care about Bose-Fermi mixtures. They stand at the heart of a lot of interesting, intriguing physics. And so we would really like a theoretical tool or a computational tool that will allow us to study these different things. So the key question in this presentation is, can we create an exact, and I would say here, quantum Monte Carlo method that allows us to study these mixtures at finite temperatures? So the starting point for developing a technique is your model. So the model we're going to use is the Bose-Fermi Hubbard Model, which is a combination of the Hubbard Model and the boson-Hubbard Model. There are 4 key terms, just to review. There are hopping terms, which are kinetic terms describing the hopping of the bosons and the fermions from site to site. There's a boson-boson repulsive term, which describes the repulsion among bosons on the same site. There's a Bose-Fermi coupling term, which describes the coupling between the bosons and the fermions. And then there are chemical potential terms that set the number of bosons and fermions on the lattice that you're studying. So this sets the filling. So depending upon whether the coupling term is negative or positive, you'll either form composites of bosons and fermions together, or you'll form composites of a fermion basically coupled to a hole. So the fermions will be coupled with holes. And by simply tuning your lattice and using Feshbach resonances, you can basically explore the whole range, the whole parameter range of this model.
Sorry, I don't know what you mean by a hole.
A hole just means that it's more likely for the fermion to be on a site alone than with a boson. So,
I mean, in some of the wells you've just drawn one particle, and some wells you've drawn a particle with a hole. What's the difference?
right. So just to be distinct, so where am I? Yeah, so this is essentially the same as with a hole. Yeah, I should be clear about that. Yeah, you're absolutely right. There's no difference between that. It's just that this is the idea is that that's just much more correlated to be with a hole. But yeah, there's no difference in the diagram.
There's no interaction terms among the fermions?
You can certainly put on in interaction terms. What I'm assuming here is that we're working in the spin polarized case. So we've got a magnetic field. We're working spin polarized. But there's no reason that we can't put them in. It just complicates the formalism I'll show later. So there are many previous techniques that handle this model and can be applied to this model. But the key point is that none of these techniques is general. None of them applies to all dimensions, to all types of mixtures, to all different parameter regimes. So for example, exact diagonalization, which is the workhorse that many people kind of use as a benchmark, can only apply to small clusters. And that's because the Hilbert space grows very rapidly. Things like the worm algorithm, which is somewhere here, really can only readily be used for bosons. And so far, we're still awaiting something for fermions. And so what we need is a general piece that completes this puzzle that allows us to study any system for any dimensions in any parameter regime. And so that's what we're trying to construct. Sure.
The part in blue, I can't really see
Oh.
the
It just says worm algorithm for bosons.
Okay, the worm algorithm is used for fermions.
You could use it for fermions, yeah. So far, I haven't seen any combined formalism. And of course, there are also
For both Fermi and Bose.
right, and then there are also obviously some issues with the algorithm for fermions, right, at low temperatures.
Okay.
Right. Okay, so none of these techniques are general, so what we're trying to do is create a general technique here. And so the hint to the solution that we took is actually from the seminal paper on the Auxiliary-Field Quantum Monte Carlo technique. So Black-and-Beckler, Scalapino, and Sugar first developed this, the auxiliary field technique, and they actually developed this in the context of looking at coupled Bose-Fermi systems. So the original idea was, why don't we look at these mixtures? Except I really haven't seen any applications of the idea of mixtures since that original paper. And so we thought, why don't we take this idea and try to expand it to studying the Bose-Fermi Hubbard model. So our formalism differs from theirs, but they originally did come up with an idea for coupled systems in I believe, nuclear physics. And there turns out to be a few techniques that are on the market for auxiliary field. So we're all familiar that at finite temperatures you can perform auxiliary field for fermions. What you can also do is perform it in the ground state for fermions and for bosons. So the boson algorithm is just a regular projector quantum Monte Carlo scheme. The fermion algorithm is again just a projection scheme, except we use constrained path to control the sign. The key missing ingredient here, though, is that we don't have a finite temperature boson algorithm. So there's nothing that exists here. And so the route we took to forming something for bosons and fermions is to create a new algorithm that fills in this blank, and then combine it with the fermion version to form a formalism for both on the same footing.
Why is boson harder than fermion?
So it's not necessarily harder. I will show you, I'll present the formalism later on that shows you what goes into this. It's just that nobody really used this formalism to do it before. Nobody's done it before. And I guess the key piece here is recognizing that you can actually express the boson partition function in terms of determinants. So nobody's done that before.
Presumably, those determinants due to condensation become, or the matrix become more conditioned faster than we have this fermion.
Absolutely.
And
That's right.
In fact, so Bose-Fermi mixtures actually is being studied, has been studied for a long time in a way, if you think of lattice QCD as a Bose-Fermi mixture.
That's right, yeah.
But the bosons don't have a chemical potential in that case.
That's right.
So and they gauge fields. So
Right. Yeah. So I'll go through why things are actually harder, but people haven't really taken up this approach before.
But the Hubbard Stratonovich can be used for both.
Perfectly valid. Yeah. So I'm going to go through that in a second. Yeah. There's no reason that you can't do it. All right. So just to remind those who are somewhat unfamiliar with auxiliary field quantum Monte Carlo is very much like classical Monte Carlo for the Ising model. So you try to sample various fields at sites, and by sampling them according to the partition function, you can then evaluate various observables as a function of these field configurations. So for the Ising model, you have only up and down spins at each site. What makes AFQMC a little bit more interesting is that you have a number of different fields at sites that basically sample a Gaussian distribution, so they can point either up or down and have various magnitudes. Also, because you're dealing with a quantum algorithm, you not only have fields at each site, but also at every imaginary time slice when you break up when you do a Trotter factorization, basically. All right, so starting with the formalism, as we're all familiar with, to evaluate finite temperature observables, you have to sample the partition function. The partition function is the trace over a density operator, and this operator is a long time operator, so it has to be broken up into short time operators to get reasonable expressions for these things. And you can apply the Suzuki-Trotter factorization to break up the short time operator into kinetic and potential pieces. Where these fields come from in AFQMC is from this potential piece. This is a two-body piece, and in order to apply these operators to the determinants and get determinants back, you have to reexpress this as a one-body operator. And so the way we do this, just to remind you quickly, is through this Hubbard Stratonovich transformation. Here I'm writing the continuous form, which is key, I think, for many fermion simulations. You use the discrete form because it yields better results in the end, more converged results. But here we'll be using the continuous form. And so every potential operator, at least the ones we deal with, can be written as a square of one-body operators. And then these can be, if you take the exponential of the square, this can be written as an integral over fields times a probability. This is a Gaussian probability of sampling a given field times a one-body operator. So this is a field times the original one-body operator we had here. And so you can substitute this for the potential propagator, substitute this back, and then you eventually wind up with the partition function, which is an integral over all fields times product of Gaussian probabilities times a trace over one-body fermion operators. And key for our subsequent discussion is that when you take this trace, you get a determinant of I plus a product of matrices that correspond to these one-body operators. So this is the key form for fermions. What changes in our formalism is here. Instead of taking this trace, we're going to take a different trace. All right, so I don't think I have to go through that here. So when we're creating our boson algorithm, what we have to keep in mind is what traces we're taking and also what Green's functions we're evaluating. So I'm not going to go through the formalism here today. It takes a few pages to do this, but you can basically convince yourself that while the fermion partition function is in some sense proportional to the determinant of I plus a product of matrices. Here for the bosons, after you take that trace, it's a determinant of I over I minus the product of these matrices. So you're flipping the sign, and you're also taking the inverse. Whenever you're coding this comes into play. The Green's function can also similarly be evaluated. Here we're just flipping the sign. So here we have I over I plus, and here we have I over I minus, a product of the matrices. So these are the two things that you have to keep in mind for the boson algorithm. And if you don't want to go through the derivations, you can just convince yourself that this is basically right by comparing the interacting case to the non-interacting case. So we all know this non-interacting case from, I don't know.
Yeah, but it's exactly the same thing. In fact, if you diagonalize the Hamiltonian, the one-body Hamiltonian,
absolutely.
It's exactly what we learned in StatMech 1.
Absolutely, same thing. Yeah, but this is the key thing that we're using. Yep. All right, so for Bose-Fermi mixtures, what we have to do is then break up the Hamiltonian. So in order to do our Hubbard Stratonovich transformations, we have to have squares of one-body operators. Here we see a coupled term. This isn't a squared term, so then we just have to rewrite our Hamiltonian here. So we rewrite our Hamiltonian, and we get two squares of terms. Again, I'm not keeping the fermion-fermion interaction term, just a simplified notation here. You get two squares of terms, and therefore we have two Hubbard Stratonovich transformations. And doing the continuous transformation, you should note that we end up with one-body operators that are complex. So in general, UBB, well, UBF can be positive or negative. If it's positive, we get a complex term here. If UB is greater than UBF, we also get a complex term here. So these are complex, and I'll come back to that in a second. They're not complex in all cases, but in some cases they are. So again, now we just have to, for the Bose-Fermi partition function, we take the traces and then substitute the correct determinants for both terms now. So we get a product of two determinants now whenever we're sampling these things. And again, since we have two Hubbard Stratonovich transformations, we have two sets of fields, a Bose-Fermi field and then a boson field. And then if we did for fermions, we'd also have fermion fields.
Can you show the Hamiltonian again?
Yeah, there you go. So I should say I lumped all the one-body terms into the case. So I'm just cleaning up the notation here.
So the linearized Hamiltonian, does it separate into a boson part plus a fermion part?
Oh, sorry, where are you talking?
So in the so the one-body Hamiltonian.
Yep.
Through the HS transformation.
Yeah. It's still, there's a boson part and a fermion part.
Okay, yeah.
But you seem to have a boson part and a boson-fermion part.
Sorry, you're talking about this term?
No, at the bottom. So after you transform, after you linearize,
Oh.
you have a boson part and then a boson-fermion
Okay,
part.
yeah, so you can see that these just break up, right? So you can just lump all the fermion terms together and the boson terms together.
It's only boson and fermions, there's no compare.
Right,
Only
so-
boson and fermions.
Right,
The
so
sigma is BF.
that's right. Yeah, everything's decoupled. The thing that basically controls the coupling is the sigmas that you're sampling.
And the chemical potential for spin up and spin down is the same for spin up fermions and spin down fermions.
Right. So again, I'm just going to handle the spin polarized case. But yeah, I'm assuming the chemical potential is the same. But it doesn't matter. I mean, if you make it imbalanced, you just have to deal with the sign problem, right?
So in this case, you want the fields to be complex because you have an I.
I don't want them to be complex. I wish they weren't.
You want the square root to be like I.
Right. So that would be the best case situation. But I'm not assuming that case here. So that's the formalism. So just to go through this, and I should say in the results I subsequently present, this doesn't assume a huge role. We also have to deal with the sign problem because we're dealing with fermions, and what we use is the constrained path approximation. So in the constrained path approximation, you have determinants that have varying values as you sample paths in imaginary time. And these paths can touch the 0 point. And in the constrained path approximation, we assume that all paths that cross the 0 line will be canceled. So we get rid of walkers that have such paths. And the basic idea behind this is that once walkers touch the 0, they may either become positive at the end of the day or negative, and this creates noise. So I'm not going to say that this is an excellent approximation, but it works in many cases. You can look at publications by my collaborator Zhang for more information about that. And to deal with the propagators, we also use what's called the phaseless approximation. So just to remind you, this can be readily complex. For the boson-boson repulsion term, we usually treat the bosons as repulsive. So we get a complex propagator. When this happens, the weights of our walkers populate the entire complex plane. And so what we have to do is basically project the weights. What we do in the phaseless approximation is we project the weights onto the real axis. So the severity of this approximation depends upon exactly what coupling strengths you're using. So what are your UBs, what are your Bose-Fermi couplings? And it also has to do with what other modifications you're making to your Hamiltonian. So I'll show you one quick modification. There are other modifications that I've played around with and made. One very important one to get the results that I'll show you is basically subtracting off mean field terms. So you can estimate the densities of the bosons and fermions on each site using mean field theory, or if you have a better theory for what these should be, you can do that as well. And when you subtract off these terms, you just vary your Hamiltonian. You can fix your Hamiltonian to do this. And then you end up with propagators where you're basically taking some complex number and multiplying it by the difference between the real density and then the mean field density. And so this basically, in some sense, controls your phase. It at least mitigates the phase that you're seeing if these are close, assuming they're close. If these parameters become large, you're still in trouble. However, this helps things a good bit. So with this, you can then project onto the real axis and do a fairly good job. But this is actually pretty key, that you need a way to basically decrease the magnitude of these terms in these exponentials. So another way that Shiwei has certainly looked at is also modifying these phases as well. So can you make these fields also slightly smaller as well? I haven't played as much with that in this work, and the results I'll show you. However, that's another way that you can perhaps mitigate the phase problem here too.
I think this is a point that maybe we should continue to discuss in the discussion sessions if people haven't had enough of this. I don't know, it makes me very uneasy to a phase. I understand this is what people do, and I'm not trying to disassemble your talk. But I mean,
Sure. Yeah.
Well, the part of doing something with the phase so that you don't have a sign problem.
Yeah.
What is the phase problem?
Projection.
No, the Schitt's main field is fine.
Okay.
Yeah, but the phase. I mean,
Well, it's an uncontrolled approximation. So
yeah,
That's
right. It's an uncontrolled.
if you have some
Absolutely.
small space where you can test it and see it's good.
Is nested
Yes.
phase
Yeah.
not equivalent to using the phase from a trial function that obeys some limit as you go to the exact trial?
Absolutely, you can do that. Yeah. So I'm not going to go. Okay, so I mean, you're talking about the phase of the whole thing. That's correct. Yeah, you can do that.
Right now.
I'm not doing that right now, but you can certainly do that. If you had a very, very good approximation for what phase you expect, then you can set that up. I haven't spent the time to do that right now. Okay, so that's the basic formalism. Let me show you some quick results. And this is just a follow-up on the discussion that we had earlier this week. What happens when you have this phaseless approximation, and compare this to the exact results. So QMC here, I should say the phaseless and the QMC are both QMC techniques. It's just that QMC here denotes the exact technique, no approximations. Phaseless denotes with the phaseless approximation. ED is exact diagonalization. So you put your number of bosons down on the lattice and you diagonalize the Hamiltonian. I should note that I only look at small systems here. I'll be presenting small systems when I compare to ED, because ED becomes exhausted extremely quickly, and that's sort of part of the problem with bosons. You can only really start looking at handfuls of sites when you look at reasonable occupancies in ED, because otherwise your Hilbert space grows very, very, very quickly. So that's a bigger problem.
So in this case, there's no sign problem because the QMC works?
So in this particular case,
What do you mean by QMC? Is it auxiliary field?
oh, so QMC is the full algorithm that I outlined,
Yeah.
no phaseless approximation.
You just ran a long time in the
That's exactly right. So I'm killing the error
There
bars
is a
here.
sign problem in that.
There's
I don't
a,
see the sign problem because sign problem means that it charge better to the blast.
There's a sign,
Right.
it's not a problem.
right.
Where is the error? I don't see.
Right. So I should say there's a phase problem, which is the more general version, but it's not a huge problem at this point. And I'm beating down the error bars. I'm running this pretty hard at this point. If you go to much lower temperatures, this becomes much, much, much more evident. So you can note the units. I'm at reasonable temperatures here. I'm not at extremely low temperatures.
You can do this because it's a small problem.
That's right. Yeah, I can just kill it. Right.
So I guess the question is, at very low temperatures, when the sign is a problem, you get the correct result with the phaseless approximation.
Right. So things then begin to deviate. Absolutely. So I'm not showing those results here, but I can certainly talk to you about them later on.
But the ground state you know exactly from the ED, right? So how does the ground state energy compares with the phase?
Right, so I'm not going to the ground state here. I mean, I'm doing ED for the finite temperature system here. That's the red line here, and that's the comparison. I should note this is fluctuating only because it's not that easy also to control your average occupancy, which I'll get to in a second, which I think you guys have an answer for. So anyway, using the phaseless, we do reduce the error bars. I should say it's not dramatically, which is somewhat surprising. For the ground state case, phaseless does very, very well. For the finite temperature case, we don't see it doing quite as well. So I'm just showing you this slide because we've had this discussion before. So again, I'll do a few more comparisons, again on small systems, because that's really what we can do with ED. I'll show you other systems shortly. So here I show a comparison between ED and QMC. Here denotes exact, no approximations. And these are for varying coupling strengths. So the coupling between the bosons is given in units of the hopping. And so here I go between 1 and 3. And again, you see pretty good agreement between the ED and QMC for all of these coupling strengths. Now here I show a comparison for the same system compared to mean field theory. Sorry. All right, and mean field theory is given by this orange line. What we see is actually a significant deviation from mean field theory, even when you go to a boson-boson repulsion of 2, which is relatively small, actually. And so you see that mean field theory starts failing for these systems very, very quickly. So this suggests that mean field theory is probably not doing such a great job in many of those phase diagrams that I showed you earlier. And this is just for a small system. So there are significant differences that you should take into account.
The green curve is the outlier, and that's ED.
So this is ED and QMC. This is just for a higher coupling strength between the bosons.
I'm looking at the top curve.
Yeah.
The green curve is the outlier.
Right. This is just a larger coupling strength, right? And the mean field theory it turns out the mean field theory for the condensate fraction is actually the same regardless of the coupling strength for these kinds of calculations. So this is not an accurate result for the condensate fractions. Yeah?
So this is one boson and one fermion per well?
This is the filling, yeah. So it's approximately that per well. Does that make sense? All right. So you can also go to larger systems. I compared to mean field theory where it can be accurate at very high temperatures for varying sizes, just to show that we can go to larger sizes. We can also compare to the worm algorithm, which of course allows us to go to